Thank you very much. I really appreciate the opportunity for you guys to join with us today in regards to the IDS Diagnostics. A lot of common sense is applied here, and let's get through it and start it. This is on our diagnostics of the IDS system, and Bosch is involved with many aspects that we got to at least talk about briefly, from water such as the boiler application to cooling, which we're talking today on IDS, but we do handle geothermal, we handle package units, mini splits, many opportunities. Hot water for domestic heating, electric, gas, propane. And then we do our controls such as the BCC 100, BCC 50. So there are many aspects that we're involved with. We're going to jump into the diagnostics. So the whole process for diagnostics is you have to challenge yourself. We're quick to ask people for answers. We never grow when the answers are given to us. Our growth occurs when we challenge ourselves. We have to dig deep and figure out what's going on. Resist that quick call. Use your common sense. A lot of times, common sense is going to take you right to the location where you need to be. Understand the actual issue. Sometimes we don't really know what's going on with the system, how it works, and because we don't understand it, we go down a path that's not right. Understanding how our system works will directly affect how quick you respond to getting your diagnostics taken care of. Follow the path. Sometimes we want to deviate. Follow the path. It'll lead you to the right location. Working smarter, not harder. That's the focus of life. Be the best. Be an IDS guru. To eliminate the diagnostics, proper installation is really critical. Realizing that our problems that we have are less than 1/4%, 0.25, 2.5 units out of 1,000, 1/4%. So a lot of times it gets involved with the installation. We're going to give you some suggestions to follow through to hopefully eliminate those issues. First thing has to have the right weather conditions. We don't want to be out running refrigerant lines and pouring down rain in high humid environment conditions. We want to set the outdoor compressor section. We want to install a surge protector. There are two ones out there. There's the ICM 493, which is a great unit, and also the Supco LBK10. They both have relays involved that they lock out the units. Some of the other surge suppressors have lights, and when it trips out, it goes from a green light to a red light, but the unit continues to run. These style surge suppressors will shut down the equipment and protect the equipment once they do trip. So you install a surge protector, disconnect, wire the compressor, and then power up the outdoor unit immediately. There is a crankcase heater. The purpose of the crankcase heater is to prevent refrigeration from migrating. Refrigerant will migrate to the coldest spot. Without a crankcase heater, there's a good chance the compressor may or may not start. And if it does start, all the refrigerant that's in that compressor will turn that oil to a foam and will leave the compressor section. After you do that process, set the air handler, case coil, whatever you're going to use. Run the line set. Install the dryer. Make sure you're using nitrogen when you do that dryer. Dryers installed indoors is out of the weather. Those dryers are still canister. If you burn the paint off, they will rust. 5 to 8 years down the road, they will leak refrigerant. Due diligence. Due diligence means that you're going to protect the customer from wasted cost of repair. Paint the end bells, whatever it may take to make it right. There's no oil traps needed with our system, unless you're doing something really crazy with the suction line going up and down several times. We have an oil monitoring package that brings the oil back to the compressor. Key points here: brazing techniques with nitrogen. After we are sure that there's no leaks, our book requires 150 psi. Some people go up to 600 psi with nitrogen to confirm there's no leaks. We're then going to start our vacuum pump, install a micron gauge, and we're going to pull 3 vacuums below 350 micron. Of those 3, we'll break 2 of them with nitrogen. 2 psi. 1 click above 0 for 5 minutes. What happens is moisture in a vacuum below 70 degrees turns to ice. Ice crystals in a line set will not leave that line set. The only way to have them leave is to put nitrogen in, which is hygroscopic, looking for moisture, and allowing it to sit for 5 minutes so that ice will turn back to a moisture. And then when we run our vacuum pump the second time, we pull out some additional moisture. And then a third time. Please don't shortcut those steps. Keep in mind where we're doing this in the process, it's kind of early in the installation. We're then going to add our charge. After the third vacuum, we'll have our charge at 0.6 ounce per foot over 15 foot. The actual line set length on a IDS 1.0 is 100 feet. On a 2.0 is 150. Maximum charge on the IDS 1 would be 85 times 0.6. We'd be coming in about 53 ounces of refrigerant. And then 83 ounces on the IDS 2.0. Do not exceed the line set length. Do not exceed the line set lift. If you do so, we're asking for problems. We're asking for failures. We have limitations. We're not everything. We're good, but we may not meet every application. Proper size ductwork and airflow. Verify that it's proper. Verify that it's going to do the job you want it to do for dehumidification, for heating, and for cooling. And then last, our thermostat needs to be configured and programmed for B operation. B means we're energizing our reversing valve for heat. It defaults in AC. Our geothermal heat pumps are programmed for O, and they default for heat. They energize for AC. Always operate the equipment in both directions. So if you're installing a heat pump, make sure you check operation in AC. Make sure you check it in heat. Protect and make sure everything's working properly. The first issue we have that seems to be the big issue is thermostats. Thermostats, cycles per hour. With inverter technology, the goal is to run the compressor pretty much continuously. And so with 1 cycle per hour, that's going to eliminate a short cycling thermostat. When I short cycle a thermostat and the thermostat shuts off, there's a 3-minute delay for the compressor to equalize, stabilize. There's a 3-minute process that we run at 19 hertz. 19 hertz is roughly 9,000 BTUs. Then we move up to 35 hertz for an additional 3 minutes, which is roughly 12,000 BTUs on a 310. After 10 minutes of time pass, we're now able to ramp up and start our cooling and dehumidification process. If we shut down just 4 minutes later, this whole process repeats. And as a result, we cannot dehumidify, we cannot cool, or we cannot heat. Some of the thermostats that we're aware out there that have some issues, the Honeywell T6 Wi-Fi or non-Wi-Fi, they had a power robbing relay involved with those. And if you go with a Series 5 or Series 6, the problem's been resolved. Also, do not hook up the W1 wire on a T6, as it brings on electric heat and runs the fan continuously on a call. And it'll do that until the thermostat is switched over to cool and it has a physical call for AC. Then that electric heat will shut off. So that's kind of important on your cycling. The Vision Pro 8000 gives you opportunity for 12 cycles per hour. Again, the recommendation is not to exceed 3, but we like to see 1. 1 cycle per hour for AC, 1 cycle per hour for boilers or heat. That is the best. It has a PID loop in there. It's a self-learning loop that if it needs a second cycle, it will bring on the heat pump for a second time. It'll try to memorize that process and extend the operation next time so that it does not short cycle for that operation. We have the Nest thermostats. The Nest thermostats have 2 concerns, actually 3 concerns. The first concern is the comfort mode, which basically means that when a thermostat calls for heat, if it does not satisfy that call in 3 to 5 minutes, our second stage comes on. When second stage is energized, we're now running our electric backup heat. The complaint is our electric bills are high, and we don't see any benefits in savings with the heat pump. They have an economy mode. Typically about 9 o'clock at night, they set the temperature back in home at 10 degrees setback or droop. A 10-degree droop tends to make complaints that the house is cold at night. The heat pump cannot keep up in the evening hours. It can keep up if it's not running, for sure. And the last one is it has a momentary droop of the 24 volt on the Y to C terminal at the compressor section. It does seem to appear every 15 to 17 minutes we lose our 24 volt signal for about 3 seconds. That 3-second droop is enough for that compressor to shut down and start the sequence all over again. 3-minute delay, 3 minutes at 19 hertz, 3 minutes at 35 hertz. So that is basically 4 cycles per hour. We want to be aware of this in our thermostat so we don't have issues that point back to a heat pump that are really not heat pump issues. In our compression section, there are 4 wires at the outdoor unit. That is IDS1 and IDS2. Only 4. Not shielded cabling, no communications, 18-4 wire. What we should see across terminals Y and C at the outdoor unit is 24 volt. If we have 24 volt there, the compressor should be running. If I don't have at least above 18, 18 is my cutoff. If I'm not above 18 volts, the compressor will not run. When I'm in the heat mode, I need to have 24 volt across Y and C and B and C. If I don't have 24 volt across Y and C and B and C, the unit will not operate. That's been some service calls where people say, hey, it's 30 degrees outside. My heat pump says on the display ATL, ambient temperature lockout. For IDS1, we lock out at 40 degrees for AC. In other words, I cannot operate AC below 40 degrees. If my B terminal is not energized, it thinks you want to run AC below 40 and it will say ATL. It does the same thing on the upper end for heat. So if my B terminal is still energized when it's above 86 degrees outside, then the heat pump will flash ATL and not run AC. Just be aware of your limitations you have to operate. My W terminal on the outdoor unit is used for defrost. It gets its power from the Y. There is no R wire ran to the outdoor unit. So all the power is coming basically through Y and B. So when I'm in the heat mode and I'm calling for compressor operation, if I'm at 5 degrees or less outside, the W will be fed by Y and put power back in to bring on your electric heat or fossil fuel or during defrost. This is your basic wiring. This is an IDS2O. There are 9 wires. The IDS10 has 5 wires. Why 9 wires? We have a W1, a W2, we have our DH, we have our Y1 and Y2. Brown is always common. Must be brown, must be common to get the true operation of our system. You can see here with our OB wires where they're located at, how they go to both compressor sections. But these are the 4 wires on the outdoor system that we're talking about. These are identical to IDS1 and IDS2. Our second issue has been filter dryers. This is a cutaway. This was a contractor that's been in business for 30 years. They installed a dryer. We kind of had a clue when you first start these up, if you get a goofy restriction, you're not getting refrigerant, you can't achieve the proper hertz, there's a restriction. And he found that the dryer was plugged up, and we told him what probably happened was the tubes were inserted too deep. Been at this 30 years, not going to happen. So if you take a look right here, you're going to see the tube should end about right here. That's all the further in the tube should go. It goes all the way in and plugs itself off on this diversion tube, this plate right here. And that's a restriction. It was done on both sides where they ran the tubing in too deep. 3/8 to 1/2 inches, all the further you should be running your tube in that dryer, not 1.5 inches. Restrictions could be not purging the system. So or purging the system, I'm sorry. If you're not pulling evacuation and you're just going to flow refrigerant through the system, all that carbon and garbage can be put in the system. It can be from not using nitrogen as well. The pipe's inserted too deep, bypassing the stop. Usually that gets into worn tubing cutter wheels that are dull. It rolls the tubing down on the edge. It misses the stop. It does create a burr on the inside that needs to be deburred. And as a result, what happened in the picture can be seen. Over tightening the tubing cutter. Some of you guys out there, Hawksters. A Hawkster is a guy that cranks that tubing cutter 4 times, cranks that handle 4 times down, and spins it once. Pops the tubing off. At that point, you've rolled the edge. Again, you're going to miss a stop. Haste makes waste, guys. Slow cuts. I know there's some contractors out there that require their contractors to cut the tubing with a mini tubing cutter, a 5/8 mini tubing cutter. All you got is a finger and a thumb. There's no way to over tighten that process. Excessive weight in vertical lines. If I have a dryer and I have a line that's sitting up in the air 20 feet above that dryer, the weight of that 3/8 line pushing down on the insert of the dryer can miss the stop and create the leaks. These are issues with filter dryers. This is a steel canister. This is the edge where if you burn the paint off that dryer when you braze this in, or solder such as Stay Bright 8, this will rust over periods of time, and then the refrigerant will leak out through that dryer shell. Number 3 are TXVs. This is an exploded view of a TXV on the right-hand side of the picture. Ours does not have a replaceable power head. That's what this is called, a replaceable power head. If I have a defective TXV, it can lead up to some other issues, and we're going to cover those up here. Let's look at the exploded view. There's a bellows up here. The bellows is being pressured by the filler bulb, the filler tube. That's what this is right here. This is a small hunk of copper filled up with R410A, the same refrigerants in our system. This is strapped on the suction line. When my suction line gets warm, it expands. It puts pressure on the bellows to push these 2 pins down. These 2 pins come down. They push on this orifice plate. This orifice plate is being compressed by the spring, which is my superheat spring to close off the plate. When those 2 pins come down, it opens up the orifice right here and allows more refrigerant to flow through. When that bellows starts to get cold, this line's getting cold, the pressure drops, the spring overcomes the pressure, and it forces that orifice shut. This is my adjustable superheat spring, my control right here in the bottom. Restrictions, lack of nitrogen or no nitrogen. We must braze with nitrogen. We cannot get around that process. If we don't, we create a carbon. The carbon is black particles of carbon in that line system. They get into the screen, they get to the needle seat valve, the needle seat valve being right here, and it starts to plug up that opening and gives us grief. A lot of times that's purging the system. If I have moisture left in my system, moisture with 410A forms a wax. That wax gets itself between the spring. As the spring plugs up with wax, it cannot be compressed, it cannot be expanded. My TXV becomes unresponsive. An unresponsive TXV is almost always the fault of the technician. Sometimes shortcuts make waste. Not doing a triple evacuation with nitrogen brake. Got to get the moisture out of the system. R410 is hydroscopic. It's looking for moisture. We got to keep it dry. Broken filler bulb. If this tube breaks, what do you think would happen to the valve? If I have no pressure up here to push down on this valve, the 2 pins, this seat's going to close. If this seat closes, that means my suction pressure is going to drop. Some people think the head pressure is going to go up. Head pressure cannot go up if I have nothing going back to the compressor to compress. Usually what happens is you'll start adding charge to the system. Suction pressure is not changing. Head pressure is not changing. Then all of a sudden the head pressure spikes. It'll go up to 600 pounds, locks out on safety. And what you've done is you backed up liquid all the way from the condenser coil all the way up to the head of the compressor. It cannot take another drop of refrigerant at that point. Safety is locked out. Internal check valves can be restricted. We'll see that in the next slide. This is our internal check valve. Located over here in our picture on the right-hand side. Right here's my check valve. So my normal inlet comes through this way, which forces the check valve closed, forces it through the orifice and opening to do my AC, When I'm in heat, the suction line is going to be warm, which is going to cause more pressure here to help open up the valve, along with the check valve opening, that I can get full flow going through my TXV. That's critical that you understand the operation. This is a Bi-Flow TXV, Bi-Flow TXV, not bi-direction. On our air-to-air heat pumps, Bi-Flow is what we use. On our Geos, they're bi-direction. So if you have a low heat output, low head pressure, what are the things that we're going to see? Our display will stay at 24 hertz. It won't seem to leave that process. Now, this is IDS1. On IDS2, it would hang in around 37 hertz. It wouldn't want to leave the 37 hertz. It can be there for half hour, maybe an hour. Head pressure, usually going to be low at 200 pound PSIG, maybe 180s. We're looking for 356. We don't have 356, we're coming up short with our system. We can have a low delta T across our indoor air coil. Air temperature in 70, air temperature out 75. These are all signs of restrictions. These are all signs of the system having a problem. How do we tell if there's a restriction? We look for a temperature difference. Across my dryer, what's the dryer temperature on this side? What's it on this side? If I've got more than a 2-degree difference across this dryer, then this dryer is plugged up. It could be the carbon being pushed into the sand core. It could be moisture. It could be a tube that's been inserted too deep. Any one of those cases can affect the dryer. It could be garbage up against my check valve that's not allowing my check valve to open properly. It could be something plugged on the top that's holding that valve closed. In some cases, AC Renew has opened up a check valve issue in the TXV. Again, the temperature difference is your check. So across my TXV, in the air handler, I should have a 1-degree delta T or less. Realistically, this is a straight piece of pipe. That refrigerant is going to go in through the TXV and back out. If I'm seeing 5, 6, 15-degree difference across that TXV, there's a restriction. It's not proper. If I cannot send the proper refrigerant back to my compressor, I can't build head pressure. If I can't build head pressure, my EEV will not open. My EEV, electronic expansion valve, in the outdoor compressor section is controlled by the compressor discharge superheat. Compressor discharge superheat means that if my head pressure is running a 108, 356 pound head pressure, my compressor discharge should be around 140 degrees. My compressor discharge line, T5. If it's not seeing that, it's telling EEV stay shut. I don't want to flood back, take out the compressor. Dryer, again, plugged up with garbage would be that. The internal check valve, we kind of talked about those items as well. So low heat output, low head pressure is a concern. Anytime you have a heat pump that works well in AC and not in heat, or works well in heat and not in AC, is probably going to be a restriction of one of these two items, either the dryer or the TXV. If it doesn't work worth a darn in either of the directions, it could be a low charge or some other issue. In cooling, a lot of it's repeated again. So common scene issues, displays at 19 hertz now. We do a different number on both IDS. On IDS2, we're at 35 hertz, I believe. Suction pressure should be somewhere around 130 psi. I'm seeing typically 50 to 90 psi only. We have a low delta T at the indoor coil. Indoor coil, we should be seeing, depending on if it's a 5-on-3 or a 3-on-2, we could be as high as a 42-degree delta T across that coil. If it's a 3-on-3, 5-on-5, we could be down about 25 to 27-degree delta T across that coil. If I'm only seeing 5 degrees, we got an issue. 19 hertz is going to be controlled if my suction pressure is at 130 or lower. If my suction pressure is above 130, then that hertz will climb. The mission is to maintain 130-pound suction pressure. So that's a critical known factor of the 130. That's on IDS 1 and IDS 2. Dryers have bi-flow directions. It could be one flow. So the heat pump works well in heating mode, no delta T across the dryer. When I come back into AC mode, now I might have frost if it's radically plugged. Again, the dryer temperatures are your best check. Please don't use your hand. Use clamp-on thermometers to measure that process. The TXV that's restricted or broken filler bulb will cause a low output as well. Again, when that closes off, I starve the suction side. Head pressure does not go through the roof. I cannot bring gas back. I cannot build pressure if I have nothing coming back to the compressor. Pressure gauge readings sometimes are a little different than what our display is showing. So in AC, suction pressure is determined by the pressure transducer. The pressure transducer is located on the actual suction line before it leaves the compressor section. My head pressure is T3, which is my outdoor coil sensor. It is a thermistor. When I go to heat, my head pressure is being driven by the suction pressure is T3, head pressure is by the pressure transducer. We have one pressure transducer that's located on the suction line. That pressure transducer is reading suction pressure in AC. It reads head pressure in heat. T3 is how I get the other reading. So when I'm in AC, T3 is actually giving me the coil temperature, the saturation temperature of the refrigerant in the coil, and it converts it to the saturation pressure, and the saturation pressure is what's being displayed on my display. When it comes to heat mode, the head pressure is coming from the pressure transducer. The suction pressure is coming from T3. Again, it is the saturation temperature of the coil and converts it to saturation pressure. There's been a few cases where people said, hey, your pressure transducer is muffed up. My gauge shows 400 pounds head pressure. Your pressure transducer says 200 pounds, and we're operating this in AC. In AC, the pressure transducer does not read head pressure. The thermistor T3 does read head pressure. And if I've got 400 pounds on the gauge, 200 pounds on my T3 sensor, that means I'm backing liquid up into my coil. That would show me roughly a 50 degree of subcooling, radically overcharged, too much liquid in that coil. That is a restriction, either to dryer or the indoor TXV. Indoor TXV will usually have frost on the valve. That means the valve's not operating as it's supposed to do. It could be moisture, it could be wax, it could be carbon. Going back to the proper install techniques can eliminate a lot of issues down the road. We've had some gauge issues with the yellow jacket low loss fitting. This is a yellow jacket low loss fitting here off to the right lower hand side. Quick connect style fittings, sometimes they don't depress the plunger enough. We've had cases where people have gone out and we're going to change an EEV. They called me on site and said about the change in EEV in the summertime. I said, please don't do that. It probably is not the problem. What they found was 185 suction pressure, 220-pound head pressure. And they said, the system seems to be running. I said, what is your actual display showing? What is the LED display numbers 11 and 12 on IDS 1? 11 being suction pressure, 12 being head pressure. Came back, said 130 over 260. And your gauges are showing what? 180 at 220? With all due respect, I'll believe the electronic display over the gauges. The guy was pretty adamant, saying, no way, these are brand new. I just bought them yesterday. New gauges, low loss fittings, hoses. I said to the gentleman, do you have your old stuff still there? He said he did. I hear him going over the truck, disconnecting the new stuff, putting on the old stuff. All you heard was son of a gun coming across the phone. The new stuff was not reading accurate. Sometimes trust your gut, sometimes follow a path. If the digital readings are showing a number and your gauges are different, something's going on. Electronics are usually pretty accurate. Not saying they can't be muffed up, but you might want a second set of gauges just to confirm. Voltage readings. Our IDS1 has an upper limit of about 28 volts on the secondary side. And I'm going to say about 10% of the time we had issues if we were above 28 volts. The other 90% didn't have an issue. But if I do have 28 volt above my upper limit, sometimes our IDS1 will go into almost like a limbo status. It doesn't know what to do. It will not respond. There's been times that that'll trip an H4 code. The H4 code is one that's universal in IDS1. It no longer is seen on IDS2.0s and the later versions of IDS1.0. If you have a high voltage, it may require you using a step-down transformer, a 277 24 volt. When you think of a standard transformer, a 240 to 24 volt, that's a 10-to-1 ratio. If I have high voltage, my voltage is going to climb. Volt amps, such as this one here, might be shown as a 75 VA transformer. I'm sorry, it's 40 VA. So what that means, when I have 40 volt amps, or basically when I'm just under 2 amps of current draw on a 24 volt side, I'll put out 24 volt. But when my amp draw is less than that 2 amp, I could go as high as 27 or 28 volt unloaded. And if I get above 28 volt, in some cases that's presented a problem. So the top picture is a single transformer, single tap. This is a multi-tap. The IDS2.0 does come with a multi-tap transformer today. So there's 2 terminals in there. You can plug on a 208 or 240 volt, choose your voltage tap, and that'll set your secondary voltage more in line to work through all aspects of the primary voltage. We've had cases with the REM UV disinfectant bulb. It's caused us grief. I understand now that they are supplied with their own transformer. Sometimes people try to save time by hooking into our transformer. When you make that connection to our transformer, we've had 2 cases where they've actually backfed. Apparently a thermistor inside that bulb, a diode. I knew I'd come back with it. Sorry about that. A diode in the bulb is not blocking the reverse flow of electrons, and we're putting DC voltage across our B terminal in excess of 100 volts. That 100 volts is in excess of 100 volts DC is what's used to light up the bulb in that system. It's a high voltage DC signal. And it's taken out boards, it's taken out a couple of our compressor sections. So please be cautious with the accessories you add. When they come with their own power supply, use their own power supply. Don't cut past and figure, well, it's tied into the existing 24 volt system. We have Vaporware with our current sensing relays for filters. We have condensate pumps that tie into our system. If you're seeing anomalies, sometimes disconnect all that stuff and start over. Check your grounds. Grounds are critical. Grounds are another issue that can present problems with voltages. Subcold and superheat issues. So this is kind of cool on IDS2.0. We can actually read our subcooling and superheat from the digital display. On IDS1.0, I can get most of the information from that display, but I still have to use clamp-on thermometers. So in this situation here, we have our, for superheat, our TH, number 6 is our compressor suction line temperature. We would need number 9, our evaporator pressure temperature, and number 12, our evaporating temperature. So we have the temperature, we have the pressure, and we actually have our compressor suction line temperature. So I can actually do superheat right from this display. Subcooling, also available from here. I have my number 7, which is my liquid line temperature. My number 10, which is my condensing pressure. And number 14 is my condensing temperature. So these items are found on IDS 10, but we don't have a TH or a T3L. These two thermistors are proprietary to the IDS 20 and not found on the IDS 10. Subcooling. Good news, when a charge is weighed in, it's almost always on the money. So if you weigh the charge in, and we're going to take actual line set length, not equivalent. If I have 5 elbows, I'm not going to add an additional 20 feet of worth of charge. If I take those 5 elbows and I straighten them out, it equivalates to about 2 inches of pipe, maybe 1.5 inches. So we don't add the charge for equivalent length, we add it for actual length. On IDS 10, we always do subcooling first, then we do superheat. On IDS 20, it's checked second for subcooling, and we do superheat first. Why? IDS 10 has an adjustable TXV. IDS 20 is a non-adjustable TXV. And the IDS 20, the only way to adjust the superheat is by tweaking the charge, adding additional charge or less. Even if the subcooling is off on 20, if the superheat is dialed in, that's what we live with. What can happen on the IDS 20 is you can have a system installed on a 55, 60 degree day. The charge will be weighed in and adjusted for a 60 degree day. If you go back on a 90 degree day, what would you expect to see on subcooling? Would it be low? Would it be high? Or would it be the same? The answer is it'll be low. How about suction pressure? I'm sorry, not suction pressure, superheat. Will it be low, the same, or high? The superheat will be high. I don't have enough refrigerant to keep a solid head of liquid up against the TXV. As a result, I'll probably drift a little bit. That's acceptable. We understand that with IDS 20 that there will be changes. What you need to do is on the cover, write system installed and charged on this temperature, on this degree day. So when you go out as a technician and you hit that on a 90 degree day and it looks like it's a little undercharged, you can say it's probably right. It's correct. If you adjust the charge for a 90 degree day and it's 55, 60 degrees out, now it's going to look radically overcharged. So when you're doing this process, you adjust the charge for the date of install, for the temperature of install, note it, and then as you go out on diagnostics, if it's the same temperature, you should be looking good. If it's below that temperature, it might look a little overcharged. If you're above, it might look a little undercharged. With the IDS 10 with adjustable TXV, we adjust the superheat based on our suction line length. As a result, it doesn't drift. It's a lot more accurate. It holds in there a little better with the IDS 10 adjustable TXV. We have our buttons on our board. So this is a 3-ton. We can see on the right-hand side where it says check and force. If I want to go through my 25 parameters, I push my check button and I can read the parameter. If I want to force this into checking my subcolon superheat, what I do is I hit the force button. The force button's the one on the end right here. I hit that for about 1 second. It puts me in force mode. When I'm going through this process to do my subcolon superheat, there are a few parameters that need to be met. The first one is the outdoor temperature. Got to be above 55 and below 120. If it's not 55 degrees outside, I cannot do my subcolon superheat check in AC mode only. I do not do it in heat mode. It's AC. If it's above 120, you probably want to move. It's too hot where you're at. Indoors is 70 to 80. If it's below 70, I cannot check my subcolon superheat. And if it's above 80, I cannot check it. And my last parameter is it has to be in force mode. That means my force button has to be pushed for about 1 second. And then let that unit run 20 minutes in that force mode to stabilize to check subcoolant superheat. If I put this in force mode and 2 hours of time pass, it'll go back to normal operation. So if you forget to take it out of force mode, it will set itself back into normal operation. We have some dip switches are shown here. We'll cover them up later on in the system. Board diagnostics. So the board has been pretty good. Safety is a major concern, guys. I can't talk enough about safety. One of the things that keep coming back to me was there was a contractor up in Canada that went in to service a heat pump. It wasn't ours. It was just a story that's told where we know with resilient mount motors, there's a rubber block that isolates that from case ground. There's a ground wire that normally goes from the motor itself to the motor housing or the fan housing. The ground wire was missing. The guy put a hand on the motor for some reason and touched the housing. He's no longer with us today. Realizing the actual current draw across the heart, 50 millivolt, 50 milliamp, it's very, very small. In that situation, it shuts down the heart. You pass on. The object is to work with one hand only, working with electricity, put the other one in your back pocket. Our system has a way to verify that we've dropped our voltage on our DC down to less than 42 volts. That's a recommended safe. Normally when all the display goes out, all the LEDs, everything's dark, you're below that process, but you can verify that. On IDS 10, we have our P2 and P4. P2 and P4 is this red wire and the blue wire. Red and blue. If I measure across those terminals and I'm above 42 volts, let it be. If it's less than 42 volts, then you're okay. On IDS 2.0, there's a fan connector up here, very similar location, and it has terminals P and N. You go across terminals P and N. If it's over 42 volt, leave it be. If you're below 42 volt, then it's safe to go. If you want to check out a board, this is part of the bridge assembly. The bridge assembly in this one is located right in the middle of the board here on the IDS 3.0. On the IDS 1 3-ton, I didn't mean 3.0, it's the IDS 1 3-ton system. So what we do is we take our incoming voltage across L1, L2, incoming voltage with the system in standby, it's not operating. And I take that voltage times 1.41. So if I have 240 volt here at my terminals, I take it times 1.41, I would see about 339 volts DC across these two terminals here. If I'm not seeing that number within 10% of 339 volts, then that means my board has a bad bridge. The board needs to be changed. It's that simple. If you don't have the proper voltages, the board is junk. Don't go any further. Don't need to do that process. Before we change out a defective board, we need to verify the compressor is good. So we have our terminals U, V, and W. Terminals U, V, and W. And we need to pull those terminals off. So we're located right here on the board, U, V, and W. And they're marked. So when you pull the wires off, you can put them back on there. And you measure the ohms across U to V, U to W, and V to W. You need to be between 0.5 and 1.5 ohms. If you're below 0.5, the compressor is shorted. If you're above 1.5, there's a problem with the winding. It's partially burnt. Then we got to go across U to ground, V to ground, and W to ground to make sure that we're above 1000 K. If we're not above 1000 K of ohms, there's another problem there as well. The compressor is shorted. If you don't check that compressor and make sure that it's good, you put a new board on without verifying the compressor is good or bad, the compressor is bad. Before the compressor physically runs, the board will be gone. That can also continue on with our fuses and our heatsink paste in the bottom. So we do have a fuse on the IDS 10 boards. They're located beside this little transformer up here on the top. It's a small 5 millimeter by 20 millimeter 3.15 amp fuse. On the 3-ton, that takes care of the outdoor condenser motor. On the 5-ton, it takes care of the crankcase heater and capacity. In other words, on a 5-ton, if that fuse will blow, it has a tendency not to ramp up to the right output capacities. Most of the time, that would be a crankcase heater when there's been a problem. I'm aware of one fuse on a 3 and one fuse on a 5-ton that present an issue. It's not a common issue. Heat sink locations on the back of the boards on the IDS 10 3-ton. There are 5 screws that are here, 2 up here. These all need conductivity paste. These are what clamp on to the actual aluminum block. And this picture is a little hard to see on the edge, but we have a cradle that comes with the board. Do not take the cradle off. Leave the cradle stay. Disconnect the wiring, and there's 2 little clips on the top of the board that are located up here on the top. Push those clips and you can take the whole board out of the cradle and then place a new board in. It's a lot easier and you don't have to take the caulking and everything else off that board at that process. On a 3-ton, there's 5 screws. On the 5-ton, there's 4. That is critical. There's been one case where a guy went in, the first contractor changed out the board, only put 2 of the 5 screws in. The sequential change of the boards as that board went bad with other contractors, they assumed only 2 screws were supposed to be there. They kept putting 2 screws in. They kept taking out the boards. All 5 screws must be in location. 2 of the vertical screws that'd be on these ones right here. These 2 vertical are the smaller 3 millimeter. These are 4 millimeter screws. They cannot be interchanged. This is a 5-ton board. This is the bridge we talked about in the 5-ton. On IDS 105-ton, there's a kit today that changes the power board, the bridge, and the display board. All those must be changed. This is showing a picture of where the conductivity grease is applied across the 3. They have to be on their level. It has to be the right conductivity grease, not well grease they use in a well to put a thermal sensor into, but an electronic style sensor. Always compressor ohm, like we talked about, all screws must be installed. If one board's bad on a 5-ton, they all get changed. The good news on IDS 2.0, there's only single boards in the 5 and 3-ton. IDS 1 has a single board in it as well. And there was some rumor that the IDS 5, IDS 1 may get changed over to a single board down the road. As of right now, it is not. If you don't take care of these conditions where you clean off the old conductivity paste, put the screws in, just powering up the board, usually within 5 minutes, it'll be gone. The heat sink on the original block, this is here. This is what we talked about, pulling off the excess paste. This is the cradle that board snaps into. There's 2 clips down here to hold the bottom in. There's 2 clips right here in the top that you push and the board snaps in place. If you take this cradle off, you're going to have to take out all that caulking around that board. So just pop off the board out of the cradle. Don't take the cradle off. There are different diameter screws. Dehumidification issues, thermostats we talked about, short cycling. That is probably our #1 issue we have with that process. Dirty coils, residual, such as oil-based, have cases where water will not leave the coil. So if you have an oil residual on this coil, it doesn't seem to be dehumidifying. We're not getting any moisture out of the condensation drain, but it's cooling the air. Try cleaning the coil. We've had a couple cases where on horizontal applications, water may drip off the coil into the bottom of the pan, not in the condensate pan, but under the bottom of the panel, and cause condensation on the outside. That's been an issue with dirt. Airflow issues. If I exceed 500 foot per minute velocity across the coil, I will wick water off my coil. Having the proper airflow, proper duct size is very critical to keep that velocity below 500 foot per minute. If you suspect you're having an airflow issue with the fan running, pull off this return air door on the fan coil over here. Take off the door with the fan running. If I can't pull that door off, it feels like it's super glued on there. You're starving for return air. If that air panel falls off very easily, then you could have a supply air problem. Our coils we're targeting are going to be 37 degrees, which is available for all applications, but usually more for Unico and Space Pack, the high velocity systems. Why? They have a fiberglass duct, 2-inch sound attenuation tubes that are insulated with 2-inch fiberglass. Diffusers are plastic. They can handle a colder coil temperature. If I put 37 degree air into a metal duct that's not insulated well, we'll have mold, bacteria, fungi, all kind of different growths on the outside of that duct in unconditioned spaces. Department of Health will be there. Not a good position to be. 47 degrees is what it comes with stock. That's our normal setting of temperatures. Defrost, number 11. Sometimes we don't have our switch set up right. There's a 2-pack dip switch, SW5. If you're in snow country, it always must be on. If it's an older style, one of the early style IDS 3s or 5s, it has a J2 jumper, not a dip switch. There is a software update that can be applied. By now, I think that should have been done. We shouldn't have the issues in defrost. If I come up with only a partially iced coil, the top part of that coil is iced up, or the bottom half, or the middle, then that's usually a charge issue. We lost charges. In some cases, the locking caps are recommended now. It's a federal mandate that all should have them on. We've had people huffing refrigerant, carrying refrigerant hose in their car. They hook on, they sniff it. I guess it's an oxygen scavenger. Strange cases, we've had people losing 2-pound refrigerant a week in the system, could not find the leak anywhere. They put the locking caps on, problem went away. Follow the path. Don't look in deeper. If there's not a leak, probably not a leak. Usually there's an oil residual around the case where that happens. This is your SW5, the 2-pack. The first switch allows my defrost time to operate quicker, and my second switch allows an extra 60 seconds if needed to clear the coil. It doesn't mean it's going to do that all the time, only if it's needed. So we kind of brought that to a close, and I'm running a little late. Let's see if we can get your questions answered.